Okay, hello everyone. Welcome to the RCNP course. And today we are going to introduce the topic, which is STP, the Spanish Tree Protocol. And firstly, let's see some basic STP concepts. The local area network generally has redundant links. A method is required to block the redundant links, remove the path loops, and can automatically switch redundant links to the forwarding state when necessary to restore the network connectivity. So we can use the Spanish Tree Protocol to do this. Spanish Tree Protocol includes STP, RSTP, and MSTP. These are three different working modes of the Spanish Tree Protocol and are suitable for different scenarios. In this course, we're going to introduce them one by one. Firstly, about the STP, let's see the function of it. STP is a protocol used to remove loops on a layer 2 network. And to prevent the loop at layer 2 network, firstly, we should block some redundant links. In this way, we can remove some possible path loops on the bridge network. For example, like this. On the figure, you can see actually we have some loops on at the left, right? And to solve the problems caused by loops, we have blocked some of the ports. For example, we have blocked these ports on SW4, and for example, we have blocked these ports on SW1. Of course, you can also block the ports on the other end of this link. So in this way, we have got a topology as what we can see on the right. And obviously, there's no loops anymore. But if we just maybe physically disconnect these things, it causes a problem. Even we have solved the problem of loop, but if there is some fault occurs to the network, for example, now, if in this case, this link is faulty, so we have lost the connection between SW2 and SW3. It would cause some communication lost in the network. So we cannot just directly disconnect the physical links. We can maybe block these ports. So the word here we use is block, because when there is some fault occurs in the network, we can still activate the redundant backup link. And in this way, we can restore the network connectivity when necessary. This is the function of STP. And then let's see, to achieve these functions, we should know some concepts. First is the bridge rules. In STP, we have two different rules of bridge. As you can see here, the root bridge and the specified bridge. Specified bridge is also called non-root bridge. Okay, so root bridge, non-root bridge. And for all the ports, they have three different rules: root port, designated port, and alternate port. Based on the SPA, shortest path algorithm, STP creates a non-loop path through the following procedure. So to achieve or to create a non-loop path, we should do some elections. Firstly, elect the root bridge, and except the root bridge, all the other switches are non-root bridges. And then elect the RP, elect the DP, elect the AP. About what are they? For example, what is AP, or how to elect the AP is the content what we are going to introduce. Okay, and to do the election, actually we should maybe take some parameters into consideration. So then let's see the parameters we should know. First is the bridge ID. Before we introduce a bridge ID, firstly you should know what is bridge. the bridge we mentioned in STP, you can think it's just the switch. So bridge ID, you can think it's just the switch ID, the ID of the switch. A bridge ID uniquely identifies a bridge in the STP. A bridge ID consists of the following two parts and has 8 bytes. It consists of priority and MAC address, bridge priority and MAC address. Bridge priority is the higher 16 bits. MAC address is lower 48 bits. So priority and MAC address. MAC address is easy to understand. It's just the hardware address of the switch of the device, while the priority is the value. And by default, the value is 3200 and by default, the value is 32,768. And of course, you can manually configure this value. It ranges from 0 to 61440, and which step is 4096. Okay, so it means that the smallest value is the 0, and then 4096, and then 8192 in this way. Okay, this is the bridge ID. And next is the path cost. Path cost is used to balance the advantages and disadvantages of paths between bridges. Each link in STP has a cost value. Path cost is the total cost of all links in the path. Or sometimes we prefer to call it RPC, root path cost. Okay, is a total cost of the all links in the path. And for the cost value, actually is related to the rate of the ports. You can see for different port rates and different port types, they could have different values. And for the port cost values, they have different standards. Okay, 802.1D, 802.1T, and 802.1T non-standard. You can see different standard you use, you can got different values. Okay, and what you can see here, short or long or low standard is a command related to this standard. For example, if you want to use the 802.1D, so in the command lines, you can use the commands to change it. Okay, and short is related to 802.1D. Long is related to 802.1T, and it has another mode, long standard mode. Okay, this is about the path cost. And by default, what we use is the second one. Okay, by default, the standard is the second one. And next concept is about the BPDU. BPDU is stand for Bridge Protocol Data Unit. Okay, Bridge Protocol Data Unit. And it can be divided into two types. First is the CBPDU, or Configuration BPDU. Network bridges exchange CBPDUs to obtain the parameters required for STP calculation. The root bridge sends CBPDU at the interval of hello time, and max age specifies the aging time of CBPDUs. So this is the BPDU that we periodically send from the root to the downstream switches. Okay, and the interval is hello time. And by default, the hello time is 2 seconds. The max age is the aging time of CBPDU, and by default is 20. Except the CBPDU, next is the TCN BPDU. TCN stands for Topology Change Notification. So from the name, we can know that it's triggered only when the topology changes. So yeah, it says here, a network bridge sends TCN BPDU to inform network topology changes. the directly connected non-root bridge with a changed topology sends TCM-BPDU to trigger topology updates. And in this way, it can reduce the MAC address aging time. Because by default, the MAC address table or the aging time of MAC address entries in the MAC address table is 300 seconds. So it would cause a problem. If the topology has changed, STP only takes about 30 to 50 seconds to restore the network. But maybe the MAC address entries are not refreshed because it has 300 seconds, right? So it will make the maybe network unreachable. So in this way, by using TCM-BPDU, we can solve this problem. Actually, the root bridge in the network can force all the switches to refresh their MAC address table. In this way, we don't need to wait for about 300 seconds. Okay, this is about the BPDU types. And let's see this figure. Okay, normally each switch will receive a BPDU and will send a BPDU. Okay, for example, the CBPDU firstly is generated by the root bridge, which is SW2 in this figure. And SW2 will flood this CBPDU to all the downstream devices. So SW1 and SW3 can receive it. SW1 will send it to the downstream device SW3, and at the same time, SW3 will maybe send it to SW1. This is the exchanging of CBPDU in the network. But for the TCM-BPDU, let's see it. Now, this port is 40 on SW1. And in this case, you can see both SW1 and SW3, since they are directly connected, so both of them can detect the failure of these ports, and both of them will send the TCM-BPDU to the upstream devices. In this case, the upstream device is SW2, is the root bridge to notify the root bridge that, okay, the topology has changed. Okay, this is about the BPDU types, right? The information they carry and the process of exchanging. After knowing the BPDU types, next, let's see what's the information carried in CBPDU. Okay, what you can see on this figure is a CBPDU. It contains the DMAC, source MAC. DMAC is destination MAC address. Source MAC is a source MAC address. It's quite easy to understand. And next, LT is a length of the frame. So it's a frame length. LLC header is fixed link header of messages. What we should pay attention is the payload. Okay, payload actually carries the BPDU data. And what are the data? You can see the protocol identifier, protocol version, BPDU type, and some flags, a route identifier, route path cost, bridge identifier, port identifier, message age, max age, hello time, forward delay. Okay, all this information about STP is carried in the CBPDU. And to elect the root port, the designated port, we should maybe take some of these parameters in CBPDU into consideration. Okay, and for the TCM-BPDU, it carries less information. You can see the structure is the same, DMAC, source MAC, and frame length, LLC header. But at the payload part, it carries less information. It only carries the protocol identifier, protocol version identifier, and BPDU type. Because actually you do not need to carry any parameters of the network. It's just a kind of notification, right? So the information is fewer. After knowing these basic concepts, next we're going to introduce some STP calculation process. Okay, let's see it. Firstly, is processing CBPDUs. A network bridge compares CBPDUs received over different ports with the CBPDU and determines the CBPDU with the highest priority. Then the network bridge uses the CBPDU with the highest priority to update its CBPDU to elect the root bridge and determine the port rules. Then the network bridge sends a new CBPDU over the DP. But here, I think you may get confused. How does the bridge or how does the switch knows that which BPDU has the highest priority? There must be a maybe comparison rule. So let's see it. CBPDU comparison rules. CBPDU with the smallest priority number has the highest priority. Firstly, we should compare the root ID. Okay, the root ID. Root ID represents the bridge ID of the root. Means root ID. And then compare the root path cost. Then compare the bridge ID. Last, compare the port ID. For all these parameters, we prefer the smaller values. So the smaller, the better. For example, if one CBPDU has the maybe smallest root ID, so it has the highest priority. While for maybe two CBPDUs have the same root ID, so we will compare the root path cost. If one of them has the smallest root path cost, so it has the highest priority, just like this. Okay, and next is the Spanish tree calculation task to elect the root bridge and to determine the port rules. Because you should think about this. The working method of STP is to find out a redundant port and block it. So how can we determine which port can be blocked? So we should first determine which port is the root port, which is the designated port. While for a port which is maybe neither root port nor designated port, so it can be blocked. Okay. So firstly, determine the root bridge and determine the port rules. And let's see an example. Now we have 4 switches, right? 4 switches. First step is to determine the root bridge. So to determine the root bridge, we should compare the bridge ID. And actually, for the devices, they can directly see maybe which switch has the smallest bridge ID. But to make it easier for us, for our human beings to understand, you can think that firstly, we compare the priority. Okay, so priority. In this case, we have 4 switches. SWA priority is 0. SWB priority is 8192. SWC is 32768. And the SWD priority is 4096. So which switch has the maybe the lowest priority value is obvious, right? It's SWA. But at the beginning, each switch will think is the root bridge because they do not know any information about the neighbor. So SWA says I'm the root bridge. SWB says I'm the root bridge. And for SWC, SWD is the same. Since they are the root bridge, we see that root bridge will periodically send the CBPDU, right? So let's see it. Each of them will generate and send their CBPDUs to the neighbor. So in this way, actually, you can see all of them can know the information of its neighbor, right? Because for example, SWC can receive, you can say can receive the BPDU from SWA, from SWB, and from SWD. For SWD, it's the same. It can receive the BPDU from SWB and SWC. So in this way, they can know each other very well, right? While after receiving these BPDUs, firstly, SWB knows, let's see them one by one. SWB received the BPDU from SWA and finds it has a lower priority value. So SWB will think, okay, SWA is the root bridge. While for SWC is the same, it can receive the BPDU from SWA, so SWC can know SWA is the root. But for SWA, since it cannot receive any CBPDUs that has the higher priority value, right? So SWA is the root bridge. So the result is like this. SWA says, I'm the root bridge. SWB says, SWA is a root bridge. SWC knows that SWA is a root bridge. But for SWD, since SWD cannot directly receive BPDU from SWA, so until now, SWD still thinks that maybe itself is the root bridge. Until what? Let's see. Until SWB and SWC forwards the CBPDU from SWA to SWD. So in this way, SWD says, okay, I'm the root bridge, but my priority value is higher than SWA. So SWD will recognize that, okay, SWA is the root bridge. Until now, we have finished the election of root bridge in the network. And the next step, we should determine the port rule. Okay, and we have 3 different port rules: RP, DP, AP. For RP is a port on a network bridge that is closest to the root bridge. Okay, and each non-root bridge, let's see. Each non-root bridge should have 1 RP. Okay, and to elect the RP, we just need to maybe think that which port on this switch is closest to the root bridge. And for the designated port is a port whose CBPDU has the highest priority on the link. So it's different here. So from here, we know that each link should have 1 designated port, should have 1 DP. And for the AP stands for alternate port. Okay. Alternate port is a port whose CBPDU does not have the highest priority on the link and is not the RP. From here, we know that for which kind of ports will be alternate port will be AP. For those ports that are neither RP nor DP, okay, so these kind of ports are alternate port and will be blocked. Okay, after knowing the difference between these port rules, next let's see this example again. Now we can see the task cost of each part. You can see the values here. For example, 200, 18, 20, 20, 200, right? And it's obviously it's related to their port rate or related to the bandwidth. And after knowing the value of the path cost in this figure, let's see the election process. At the initial AC state, each switch will think it's the root bridge, as what we have mentioned. So they will send the CBPDU to each other. And then in this CBPDU, of course, it contains the root bridge ID, it contains the RPC, it contains the maybe port ID, so many parameters. So when we determine the port rules, we will see firstly is the RPC, right? And then based on the parameters we have just seen on the figure, you can see some RPCs of ports. For example, the RPC of these ports For example, the RPC of this port on SWB is 38. The RPC of this port on SWC is 18. While for SWD, let's see it for SWD. Here, the RPC of this port is 218 because here is 18, here is 200, right? While for the other ports, let's see the figure. You can see here they were maybe exchange the CPBDU, and after receiving, you can see after receiving this PBDU from the SWB, SWD knows that okay, the RPC of the port on the left is smaller, which is 58. You can see this is 58, this is 218. So obviously the port on the left has maybe lower RPC value. So this is the RP of SWD. Okay. This is how to determine the maybe root port of each switch. And for SWB, you can see that okay, it can receive, you can see it can receive CPBDU from its neighbor, right? And after comparison, you can see the RPC of this port is 200, of this port is 38. Obviously, this is the RP, the root port. Okay, and the next, let's see. Since we have determined SWA is a root bridge, these three ports are the RP. So next, we should determine which is a DP. And we said that on each link, right, on each link, there should be a RP. On each link, there should be a designated port, right? So you can see these two ports are designated ports, okay? And let's see, on this link, the link between this link between SWB and SWC, which is the designated port. Firstly, we will compare the RPC and then the neighbor's bridge ID and then the neighbor's port ID, right? And after comparing these parameters, we determine that, okay, this is a DP. So we still have two links left. Let's see, on this link, maybe on the link between SWC and SWD, which port is the DP. It's the same, compare the RPC, the bridge ID, the port ID. So the port on SWC is the DP. And on this link between SWB, SWD, see, this is the RPs. And after comparing the parameters, so this is the DP. This is a DP. So we can see in this figure, we have determined the port rule of most of the ports, while we still have two ports left. This port, right, or this port, the port on SWB connect with SWA, and the port on SWD connect with SWC. They are neither designated ports nor root ports. So these two ports will be actually blocked. And once we block these two ports, means we have blocked these two links. And once these two links are blocked, so there's no loops in the network, right? This is the process that how STP remove redundant links in the network. Okay, by electing the root bridge and then root port, designated ports, alternate ports. Okay, and next, let's see some spatial scaling rules, the equivalent path cost calculation. Now, the path cost of each thing is 200. It's the same, right? It's the same. And you can see the BID of SWA, SWB, and SWC. Okay. And in this case, let's see it. Obviously, SWA is a root bridge since the priority value is 0, right? Since the And next, we should determine the root port on SWB and SWC. Since the root path cost of this port is 200, of this port is 400, so this is the root port. And on SWC it's a CM, this is a root port. Okay, so root ports. And these two ports on SWA are both designated port. So on this thing is where we should maybe think about it. Firstly, we should determine which is the designated port. To determine which is designated port, firstly is the path cost. Path cost is a CM. Path cost is CM are both 400. So path cost is a CM, and then we should compare the bridge ID. After comparing bridge ID, we think SWB has a lower bridge ID because it has a lower priority. So the port on the left is the designated port, and obviously the ports on SWC, which is connected with SWB, will be blocked. It's the alternate port. Okay, so this is the equivalent path cost in calculation in this case. And for the figure on the right, let's see it. Now we have 4 switches, and you can see some parameters here. So from these parameters, firstly, we can maybe easily find out that SWA, right? SWA is a root bridge. And next is the election of root port. On SWB, SWC is quite easy. So on SWB, here is a root port, right? The port connected with SWA is a root port. On SWC is the CM. So these two ports are root ports. While for SWD, which is a root port, the left one or the right one. So first we will compare the RPC. We find the RPC is a CM. So we will compare the neighbor's bridge ID and find out, okay, SWB has a lower bridge ID. So the ports on the left is the root ports. And next is the election of designated ports. It's just like this, okay, designated port. So in this way, which port to be blocked is obvious. The port of SWD connect with SWC will be blocked. It's the alternate port. And the last case, let's see. The last case of equivalent path cost calculation is like this. We have 2 switches, and we use 2 cables or 2 links to directly connect them. And firstly, obvious, SWA is the root bridge. And then on SWB, which port is the root port? Root path cost is the same. The neighbor's bridge ID is the same, so we will compare the neighbor's port ID. And obviously, you can see the port ID is consists of priority and port number, okay? Since we cannot see the port priority here, it means that they are both using the same priority, which default value is 128. Okay, and since the priority is the same, so E01 has a smaller port number. So this is smaller, means E01 on SWB will be the root port. And since it's a root port, these 2 ports on the root bridge is the designated port. So the port left, this is the port should be blocked. Okay. So there is word says that all the ports on the root bridge are designated ports. You think it's true or false? If it says that all the ports on the root bridge are designated ports, actually it's false. It's false because there were some special scenarios. For example, now I only have 1 switch, right? I only have 1 switch, and I use the cable to connect 2 ports on this switch. It's impossible for these 2 ports to be designated ports, right? One of them should be blocked. So this word is wrong. Okay, it's wrong. Okay, And after introducing the calculation process of STP, next let's see the port status. When the topology changes, transmitting a new CP video on the entire network takes time. Before all network bridges receive the CP video, temporary loops may exist. So to prevent the problems would caused by temporary loops, we have developed a concept which is called the state. Okay, for example, like this. Now we add a new link. And once this link is added, you can see we should detect, okay, which is the designated port, which is the root port. But since there's a loop, but I didn't maybe determine which it should be blocked, or I didn't block this port. So you can see the traffic is allowed to transmit it in this network. And this is called the temporary loop. Okay. And the temporary loop, of course, maybe some broadcast storms or unstable MAC address table, right? These kind of problems. To solve this problem, let's see the port status. Processing of CP video sending and receiving, MAC address learning, and the data sending, receiving of ports in different status is as follows. Firstly, for the port status, we have 4 types. First is blocking. Okay, first is blocking. At the blocking state, this port cannot, you can see, cannot send CP video, cannot learn MAC address, and cannot transmit the service data. Okay, and next state is the listening state. Okay, listening state can send CP video, but cannot learn MAC address, cannot maybe send and receive data. For the learning state, we are allowed to send CP video to learn MAC address, but still cannot send and receive data. The last state is called the forwarding. At the forwarding state, the port can work normally. It can send CP video, can learn MAC address, and can send and receive data. Okay, so the relationship between these status is like this. Firstly, the port is at the blocking state. And then once the port is elected as the RP or DP, so it will enter the listening state. Okay, and if the port at the listening state is elected as the AP, so it will maybe go back to the blocking state. Okay, and next after the listening state is the learning state. So let's see. To get to the learning state, the port should wait for a forward delay. Actually, forward delay is a timer, which is 15 seconds by default. It means that switching from listening to learning takes at least 15 seconds. Or the port should wait for 15 seconds. And from learning to forwarding, there is another 15 seconds. So here we can find that now we have a port, right? No matter it's blocked or what, but it's at the blocking state. And if you want to maybe open this port or activate this port and want to use this port to forward the data, you need to wait for at least 30 seconds because we should at least wait for 15 seconds, right? This is actually one of the shortage of Spanish tree. Later we will introduce it. Okay, and next here, let's see. In this case, maybe after determining the port rules, some ports are alternate ports, some ports are root ports, some ports are designated ports. So if the port is the AP, is the alternate port, you can see the status is blocking. Means these ports are blocked. And once these ports blocked, maybe they cannot forward data anymore. So there is no loops anymore in the network, right? And if some port occurs, for example, if this link is 40, So we will maybe activate these two ports. So this port will switch their states from blocking to listening, from listening to learning, from learning to forwarding. So they should wait for 15 plus 15, 30 seconds to work normally. Okay, this is about the port status of STP. And next is about the topology change. How does the STP operate the changes in the topology? Let's see it. It takes the MAC address aging time to recover a disconnected link, because if the fault occurs in the network, maybe even we have a redundant link. For example, this link is 40. Even we have a redundant link, so we should maybe go through the redundant link. But all the traffic is guided based on the, for example, as a layer 2 network, all the traffic is forwarded based on the MAC address table. But even the topology or even the path has changed. But if the MAC address is unchanged, the MAC address table is unchanged, the packet will be lost, right? Based on the wrong MAC address table entries. So it's the reason why we see that it takes 5 minutes to recover a disconnected link. To solve this problem, because 5 minutes is too long, we cannot wait for such a long time. What can we do? That's it. When the topology is changed, it takes up to 50 seconds to recover. And let's see why it's 50. Now, this is 40. This port is 40. Or even the SWA and SWC can detect maybe the fault of this port. But since these two ports on SW1 has blocked means is at the blocking status. The port at the blocking status cannot forward BPDU or cannot send BPDU, right? It can only receive. So SW1 cannot maybe send out a CBBDU, but SW3 can do this. So we can see here, SW3 send a TCM BPDU to SW2, right? And after receiving the TCM BPDU from SW3, let's see what will happen. SW2, you can see, send a TCA, because the blue arrow represents the TCA BPDU. TCA means topology change acknowledgement. It means that after receiving the notification of SW3, SW2 tells SW3 that, okay, I know the topology has changed. And at the same time, SW2 will forward the TCM BPDU to SW4, because actually SW4 is the root. It's a root. And after receiving that, the root bridge will send the TC BPDU to the downstream device, to SW2. SW2 send it to SW3. Okay, and after receiving the TC BPDU, all the switches will refresh their MAC address table. In this way, we can maybe learn the MAC address table based on the new path, right? Because MAC address table are deleted, so it's empty. And once we receive a packet, we will learn the new entries based on this packet. All right, so we don't need to wait for 5 minutes. Okay. But why is the time here is 50? You can see why time here is 50 seconds. Because once this port is done, we should wait for 20 seconds, which is max age. And after 20 seconds, we will start the TCN process, and the switch will be triggered to maybe modify the rule of the port from the alternate port maybe to a new root port, right? And from the alternate port to the root port means we should switch the status from the blocking to forwarding, and it takes 30 seconds. So in all, we should wait for 50 seconds. Okay. This is about the TCM BPDU. And the next, The conditions for network bridge to send TCM BBDO, first is a port changed to the forwarding state and the bridge contains at least one DP, or a port is changed from the forwarding or learning state to the blocking state. So in other words, TCM BBDO is topology change notification. So once the topology has changed, the switch will generate a TCM BBDO to notify others. Okay, it's a function of it. And next, in the CBBDO, actually, how do we know this is the TCN or this is TCA? Actually, is defined by the flex, okay, flex field. Let's see. At the flex field, it has 8 bits, right? It has 8 bits, and the last bits here, which number is 0, represents topology change, okay? And the first bit here represents topology change acknowledgement. So if you see, or if you check the flex field, you find that the last bit is 1. Means this is the topology change BBDO or TCBBDO. Or if you find the first bit is 1, means this is a topology change acknowledgement, or this is a TCA BBDO. Okay, it's defined by these 2 bits in the flex. Okay, and next, let's see the shortcoming of STP. First is the direct link failure. The blocked port switches from the blocking state to the listening state and learning state in sequence, finally enters the forwarding state. It means that in this case, if the direct link is 40, we should, of course, maybe open the blocked port, but it takes 30 seconds to recover because the blocked port should switch from blocking state to forwarding state. It takes 30 seconds. Or for the non-direct link failure, when the uplink of SW1 is abnormal, SW1 sends a CBBDO with root ID set to its bridge ID to SW2. After a blocked port of SW2 receives the BBDO, means you can see once the link between maybe SW1 and the root is 40, so SW1 will send a BBDO to SW2. And it takes actually 20 seconds because here is 40 and this port is blocked. So SW1 cannot receive any BBDOs in this case. So it will wait for 20 seconds. And after 20 seconds, actually the BBDO on SW1 has maybe passed the aging time. So SW1 will think, okay, now I'm the root. And then since SW1 thinks it's the root, so SW1 will send a BBDO to SW2. But in this case, SW2 find that, okay, I received the BBDO from SW1, and this BBDO has a lower priority because SW2 can receive the BBDO from the root and at the same time receive the BBDO from SW1. Of course, SW1's BBDO has a lower priority. So SW2 knows that, okay, I should forward the BBDO from the root to SW1 because it's better. In this way, SW2 will maybe open this port, open the alternate port. And once SW2 opens the alternate port, so it should take about 30 seconds because at the beginning is a blocking state, and from blocking to forwarding, it takes 30 seconds. And from blocking to forwarding, it takes 30 seconds. So in this case, when the non-direct link fault occurs, it takes 20 plus 30, about 50 seconds to recover. Okay. This is the shortcoming of STP. The recovery time of STP is too long. Okay, it takes about 30 to 50 seconds to recover a fault in the network. Okay, and for the shortcoming of STP, you can see a summary here. By default, it takes at least 30 seconds for a port to switch from the blocking to forwarding state. On a network with unstable topology, the network interruption time will be long. And when link is up and down frequently, numerous TCP BDUs will be generated on the network. Switches update the MAC address table constantly. And if we should constantly update the MAC address table, it will also affect the effective of the network. Okay, this is about the STP shortcomings. And in the next part, we're going to introduce maybe another mode of STP that can be used to overcome these shortcomings. Okay, so about this part, about STP, let's see some questions here. Which of the following statements is true about the bridge ID of an STP? Let's see it. A, the bridge with the smallest bridge ID will eventually become the root bridge after STP calculation. Obviously, it's true, right? A is true. B, the bridge ID consists of MAC address of the bridge and the priority field. When comparing bridge IDs, compare the MAC address first, and the smaller MAC address is the best. Obviously, it's false, right? We should compare the priority first, not the MAC address first. C, the MAC address of SWA and SWB is shown here. Respectively, the priorities of SWA, SWB are 32768 and 496, respectively, when SWAB performs ring networks and enables spanning tree, SWA becomes a root. Of course, no, because SWB's priority is 496, is smaller than the value of priority on SWA, so SWB will be the root. D, the length of the bridge priority field is 2 bytes, so the value of the bridge priority ranges from 0 to 65537. 0 to 65535. Actually, it's wrong, right? It ranges from 0 to 61440, and the state is 496. Okay, so here we choose A. Okay, this is about the introduction of STP. Thank you for your listening.